Okay. I think that all the signals are traversing the telephone network infrastructure in analog form. So how do we do? How can we deal with the digital form processing? Okay. So all the signals for data processing are then relayed to this. This is still in analog form. And we have this modem. Modem stands for modulation and demodulation of signals. Okay? So the analog signal is demodulated. That means it is converted into its digital form. So that's the purpose of the modem. Okay? And when data is being transmitted, the modem modulates the digital signal into its electrical signal that is in analog form. Okay? So that's the job of the modem. Analog to digital conversion, digital to analog conversion, and the modem can do that simultaneously. Okay? So let's have a look. We have this DSL modem, specifically for this purpose, for this particular access network. Okay? A long time ago, the modem for a dial-up network is very slow. It can only process up to 56 kilobits per second. That was the first time that was the first technology introduced to allow people to connect to their, to the internet. That was my generation. 56 kilobits per second, and we're happy. Whereas for DSL modem, it is able to carry up to more than 20, okay? Even 70 megabit per second, okay? And it depends on many factors. Okay? We will see what defines the speed of connectivity. So anything else? What about here? This is the telephone network. But remember, we need to connect to the public internet. Okay, let me emphasize that. That's why in the figure here we've got the ISP. Okay? This is the global internet. As depicted in the figure here, the global internet is mostly comprised of a network of routers. Okay? So the figure that you see with the cross is a router. And in the meantime, what we want to remember is that a router will be forwarding a packet to one of its outgoing links based on the destination of that packet. Okay? So little by little, we will learn more terminologies, and we will see how these technologies combine together. Okay? So the global internet is in digital form. This is in analog form. So we need to perform the conversion from analog to digital and from digital to analog. Okay? And that is the job of what we call DSLAM. Okay? DSLAM stands for Digital Subscriber Line Access Multiplexer. Okay? So we have this DSLAM component. Now DSLAM is doing the same job as a modem, except that this DSLAM can connect to thousands of homes. Okay? Your modem is only providing services for your computer at home, for your computers. You can have multiple computers. But this one can cater to thousands of requests for transmission and for encoding and decoding. Okay? Now, where can we find this DSLAM? DSLAM is placed in what we call central office. That's another term. A central office is an office without windows and without humans inside. Okay? It's a term they use to connote, sometimes they call it an exchange. Okay? The exchange is nothing but a network of routers and switches. Okay? So we have the central office, okay? The DSLAM, okay? splits the signal. Okay? All the signal again based on the frequency. Is it from 50 kilohertz up to say 1 megahertz? Those signals will go to the global internet. Okay? and that will be in digital form. Whereas signals for voice, okay, it's going to be split up, and it's going to be transmitted to the public switch network carrying voice data. So this is analog. So that's what's happening in this network. It's an access network providing internet access. Now there are some requirements for this to work. Okay? Not everybody, unfortunately, can avail of the DSL access network connectivity. Okay? There's a limitation that you should be between 5 to 10 miles. Okay? More than 10 miles, this access network is not going to work. Okay? And we will see the reasons later on. Okay? So if you look at your distance from the central office to your splitter, it should be at maximum 10 miles. And the further you are from the central office, the further the signal attenuates. It means the strength goes down. And if the strength goes down, so does the speed of your internet connectivity. Okay? So if you're so far away from the central office, unfortunately using this particular technology, you cannot avail of the maximum theoretical bandwidth. Okay? So if, for instance, you want to, I've got some links later on, want to check, can I avail of DSL? Then you need to check how far you are from the central office, and here in New Zealand, we can contact Chorus. Okay. Oh yeah.
Sorry, you said 10 miles is the maximum. Is that implying that 5 miles is the minimum, or is there no minimum to how close you can be?
Yeah, because that's how they describe it. Within 5, you're okay. 10, poor connectivity.
No, there's no minimum.
Minimum, the closer you are, the better. Yeah. So yeah, it's just because that's how they describe it in the literature. Of course, if it's 0, then you're directly connected. Then it's there. Okay, next, what else do we need to remember about this technology? Okay. Take note that between your home, this is your home, okay, in the central office, okay, you have exactly one link, one dedicated link. That means, regardless of the time you're accessing the internet, it should be roughly constant. It's going to give you roughly constant bandwidth. Okay? If you're paying for a 24 megabit per second link, it's going to fluctuate. Okay? It's going to go down a bit depending on the number of people using it at the same time, but it's not going to be that much affected. Okay? So this, we need to remember that this is providing dedicated internet access. And what else? So that's the term, you mentioned that. Okay? And here again, the different frequency bands. Okay? So this is frequency division multiplexing. You will see that there's another alternative later on. It's called time division multiplexing. And there are many ways to try and share the link's bandwidth. Okay? Again, when we say link's bandwidth, we're talking about the rate of transmission across that link. How fast can you transfer the bits per second? So some of the settings that has been used before, they keep on upgrading technology. So for instance, okay, at one stage, the downloading rate is set to below 24 megabits per second. Okay. This is the theoretical bandwidth for downloading, but in practice, typically you will be experiencing up to about 10 megabits per second. For uploading, theoretically you have 2.5, but in practice, it's going to fluctuate, go down to 1 megabit per second. And now we can explain why is this called an asynchronous digital subscriber line. Asynchronous, this term is related to the bandwidth allotted for downloading and uploading. You have different bandwidth, different transmission rates. Therefore, it's an asymmetric access. And nowadays, you will find that we have very high-speed DSL and ultra-fast broadband now. So that means if you're going to change the DSL modem to VDSL, and if you're going to upgrade your dedicated link, okay, then, and also if you're close enough to the central office, then you may avail of, let's say, VDSL. Again, not everybody can avail of VDSL, ultra-fast broadband. It is because of the distance from the central office. Okay? And when we speak of a central office, we sometimes refer to as an exchange. This is one example. No windows, it's not for humans. Okay? It's just a place for containing switches and routers. So as I mentioned before, okay, let's give more details. Okay? The maximum transmission rate, the maximum bandwidth you can avail of from your DSL access network depends on your distance from the central office. That's number one. Second, it also depends on the gauge of the twisted pair copper wire. Okay? So what we want to remember is that the thicker the wires that you use here, the better the transmission rate. And we're not talking about just one wire. Here, the wire they use, okay? So it's a twisted pair copper wire. Twisted pair. The wires are twisted to allow for the cancellation of electromagnetic interference. Okay? So it's literally twisted. Okay? One pair is equal to one link. Okay? One link. And typically within, for internet usage, you'll see a bundle of them. Couldn't remember, maybe eight pairs, something like that. Okay. So the gauge of the twisted pair copper wire, and you also need to consider the degree of electrical interference. If your home is so close to a factory and they're running lots and lots of motors could introduce electrical interference to your internet. Okay? Or if there's some other transmitting signal that coincides with your place, then that's also going to cause some electrical interference. Okay. Here's what I got from Chorus, New Zealand. Chorus actually puts the line underground. Okay. Here's what they say. Okay. If you want to avail of ADSL1, you should be up to 6 kilometers. If you want to avail of ADSL2 plus, should be faster. Okay. You can get a speed of more than 10 megabit per second. Then you should be within 2 kilometers away from the central office. And I also just want to mention, when we say speed, we're talking about megabit, not megabyte. Okay? Megabit per second. Okay? Not megabyte. So that's the unit they use. And if you want to avail of VDSL2, look, you should be 750 meters away from the central office. If you want to avail of a better internet connectivity, then you can go for optical fiber connections. But optical fibers are not widely deployed yet. Okay? Even at my home, I need to wait until October this year. I'm not living so far away, but that's the reality of that. So VDSL, and then you might be wondering, okay, DSL allows you to connect lots and lots of machines, okay? But within your home, if you live in a lifestyle block, then you need to have some sort of extenders, okay? So some other related technologies, let's say a Wi-Fi extender, such as what they call Orbi, if I remember correctly, allows you to connect your Wi-Fi, okay, even within 5,000 square meters. And if you want to check the speed of your broadband at home, these are well-known websites. Okay? highly reputable websites. Speedtest.net, okay, fast.com. And if you want to check, can you avail of fiber optic links, VDSL for your own home? We have this website that you can check. Okay. So this is just for practical purposes. Next possibility is to connect to the internet via what we call the cable network access network. It's going to be very similar. Okay? We have here digital to analog, and then to digital, and then it goes to the public internet. Very similar, but there will be some subtle differences. Okay, we're going to talk about that. Okay. This cable network access is capitalizing on the infrastructure used by cable TV. Okay? So cable TV initially, of course, allows subscribers to avail of multitude of channels, okay? Watch them, watch TV, okay? And what I want to point out here is that they're using different combinations of physical media. Okay? Earlier, we were looking at twisted pair copper wire. Here, they're using coaxial cable. In this coaxial cable, signal travels in analog form. But this coaxial cable carries larger bandwidth. Okay? It can carry both video and data. Okay? And this is how a coaxial cable looks like. It's using two concentric copper conductors. Okay? Let me just point out the similarities first, so it's going to be very easy. Okay? Analog form, coaxial cable, then we will also have a splitter. Okay? The splitter will separate many signals in this case. Okay? It's going to split the video, okay, as well as data, and also some control. Remember that we need a frequency band for uploading, another frequency band for downloading. So we can see that we've got two data frequency bands here. And if the user is subscribing to several video channels, TV channels, you can see so many frequency bands are allotted to different channels. Okay? And then of course there's this control for their own purpose. So we have a splitter similar to what we have before. Okay? And this splitter goes also to a modem. And the name of the modem, of course, so it should be for cable network access. It's a cable modem. Okay? So this is going to process the information in digital. Okay? Sorry, the computer needs digital, so this cable modem just performs modulation and demodulation of signals. Okay? What do we need to remember? Let me just finish the similar components. Earlier we've got DSLAM, okay, as the counterpart of the modem. Here we have what's the name of that? Yeah, this neighborhood junction. Okay. They call it a cable head end. There's just so many terms. Okay. This is the equivalent of DSLAM. Okay. They call it cable modem termination system. Of course, it's a modem. DSLAM is a modem. So it simply converts digital to analog and vice versa. So those are the similar components, but how are they different? Okay. This coaxial cable is actually a shared link. As compared to DSL, this is a dedicated link, only exactly for one user. This particular cable here is for thousands of users. Okay? It can be, there could be 5,000 users sharing the same link. So in that case, okay, if 5,000 people connect to the same coaxial cable, then what's going to be the consequence? If one, okay, let's look at the illustrations here. Okay, we can see that multiple households connect to the same coaxial cable. If one household is trying to transmit a signal, if multiple households try to transmit a signal, then eventually they will collide. In order to, when they collide, the signal just gets lost. It becomes corrupted. Since it is using a shared link, it is also using a multiple access protocol. This coaxial cable can carry so much more bandwidth than the twisted pair copper wire, and therefore it can be shared. Okay? So you can see that it's also using frequency division multiplexing, allowing different frequency bands for the different purposes. Let's compare the two in terms of the downstream and upstream channels. The downstream channel is shared, upstream channel is shared. So therefore, they will have to be managed by this multiple access protocol. When you look at the downstream transmission rate, it comes with a theoretical maximum of 42.8. They would have improved on this already. Okay, so this one, for instance, 42.8 during the time when DSL was introduced. Okay, 42.8 versus, you can just imagine, it's a 20 megabit per second. So this one wins. However, it is only providing a shared link. Therefore, if many people are using the same connection at the same time, let's say prime time, many people are trying to watch TV and many people are using the internet, all of them will suffer poor internet bandwidth, okay? Because there will be lots and lots of collisions along the link. So even if you're paying for this connection 42.8, you might be ending up using only 10 megabit per second. That's the reality. Anything else? Earlier we referred to the central office, so they have just a different term for it. They call it a cable head link. Okay. In the exam, I'm not going to ask you, how do you call the exchange for a cable network? I'm not going to answer these questions, but it's good for us to be acquainted. Okay, it's good for us to know that okay, they call it cable headed, they call it central office, they call it DSLAM, they call it cable modem termination system, but they serve the same purposes. What's also good about this network is that homes can be up to 100 miles from the cable head end. Okay. I forgot to mention that between the homes, between this coaxial cable and the cable head end, okay, I didn't finish. Okay. There is this, actually there's a junction here. Okay. Within a neighborhood junction, 5,000 can connect, okay? Up to 5,000 households. But between this junction and the cable modem, okay, the link is fiber optic. Okay. If it's fiber optic, then that means it can transmit information at the speed of light. Speed of light is 3 times 10 to the 8 meters per second. When you think about the coaxial cable, it's probably 2/3 of the speed of light. So that's why this technology, cable network, is also called a hybrid fiber coaxial network. Any questions so far? I think I mentioned all the important details. Next, let's look at the home network. A long time ago, when you want to put up a home network connecting multiple devices, you need to buy several components separately. Okay? So to connect our home, we need, of course, a cable. If you're going to connect to a DSL access network, it should be a DSL modem, otherwise, or it's a cable modem. Then, to provide internet connectivity to multiple devices, this modem will have to be NAT enabled. Nowadays, it's already the default type of modem. A NAT enabled modem makes use of what we call network address translation. Okay? We will learn all these details later on when we do a bit more math and computations. This modem will be providing one link, just one link. Okay? You're paying for one internet subscription, but you want to connect multiple devices. Okay? And in order for that to happen, the network address translation will compute your private IP address. Okay? You get one globally unique IP address, but inside the home, you will be using some private IP address. Okay? And in order for the packets not to collide, you have a router that connects to that cable, to that modem. Okay? Now this router, okay, can also be connected to an access point, and the access point allows for wireless internet connectivity. Okay? This is during my time. Okay? Nowadays, actually, all three are combined. But during my time, I need to buy them, these two components, I need to buy them separately. And you need to do this configuration yourself. But nowadays, modem, router, and sometimes called the base point or wireless access point, they're all bundled into one. And within the network, if you're connected to the router directly, you can have 100 megabit per second or 1 gigabit per second. Okay? If you're connecting to the wireless access point, then internet connectivity could be up to 44 megabit per second. And lately, you can also avail of 450 megabit per second. So technology keeps on improving all this speed. Next, let's have a look at an access network, an enterprise access network. So for instance, here at Massey, every time you're connecting your laptop, to the wired network or even wirelessly, eventually you will be connecting to a switch. Okay? If you're connecting to the network wirelessly, then you'll be connecting directly to the switch. Otherwise, if you're connecting to the internet, wirelessly, this is wired, wired and wirelessly, then you need to connect to the access point. But this access point is connected directly to the router. Again, this access point is usually bundled up as well together with the router, but internally they're separate. I just want to provide a bit more information. What happens is that you've got a switch. Okay. This square is a switch. Okay. This switch, in the meantime, let's try to remember that it's a link layer device. It is used for sharing a link. Okay. And to this switch, you can connect computers directly. This switch may connect to another switch, and this switch may connect to another switch, and you can come up with some sort of hierarchy. Okay. But this switch, in order to connect to the global internet, we'll have to connect to a router. Okay. This circle here is a router. A router is a network layer device. A network layer device is more powerful than a link layer device. And this router connects to, for instance, it's going to connect to our institutional web servers, our email server. Okay? We can also have a proxy server. And then this router will be our first hop router. This is what we call our default gateway. The first routers that we connect to connect to the public internet. And typically this is what how the setup is done. Between the switch and the servers, they will be given high capacity, high bandwidth of up to about 10 gigabit per second. But for the users, typically we're given 100 megabit per second. They're massive, about 100 megabit per second. But for the wireless connectivity, it depends on whether MAS is using 802.11 version G, or is it version N, or is it version B, okay? The connectivity could be limited to 54 megabit per second, or if it's using the latest, 450 megabit per second. Next, let's try to distinguish wireless LANs from other wide area wireless networks. Here, I've got some of the numbers here. When 802.11 came about in the early days, version B, it allows for 11 megabit per second. Then it was improved to allow for 54 megabit per second. Nowadays, version N, 450 megabit per second. If you're connecting to the internet wirelessly, think about it. You're not physically connected to the internet. You need to contact the wireless access point by electromagnetic waves. Okay? So in this case, you're sending everything in the air, and it can cause collision. And when we say we're using wireless networks, then that means we're using a shared medium, the radio channel. Wireless LANs will only work if you're within tens of meters, okay? And the latest technology up to about 100 meters. If you're within tens of kilometers, then you will have to make use of another technology. Okay? So for instance, if you're traveling in a car, you want to connect to the internet, then you can avail of the connection using either 3G, 4G, and in the future we have 5G. Okay? These technologies will also vary in terms of the bandwidth they provide for us. 4G provides connectivity with bandwidth of about 10 megabit per second. It's also referred to as the long-term evolution. The 5G, the internet, wireless internet of the future. Okay? Imagine in the future if you're, let's say, driving a driverless, or you're riding a driverless car. This driverless car will have to maybe, use the internet for maybe traffic updates, whatever. Okay? Driverless cars in the future will be made really, really clever by 5G, because 5G wireless, wide area wireless will allow for gigabit per second bandwidth, okay? Whereas the 4G only allows for 10 megabit per second. So that's the future. Now we can talk a bit about the physical media. Every time we're transmitting a signal across a link, this is copper wire. We're actually transmitting electromagnetic waves. If we're trying to transmit across a link that is fiber optic, we're transmitting light pulses. One pulse is equal to 1 bit. But since the speed of light is so fast, 3 times 10 to the 8 meters per second, then it can go up to hundreds of gigabits per second. Okay. Now, every time you're transmitting an electromagnetic wave across a copper or a fiber, or light pulses across this fiber optic link, this medium guides the propagation of the wave. And so physical media are categorized according to whether or not they're guided or unguided. If it's in a physical connection, it's guided. If you're trying to propagate signals, using the radio spectrum, then the signals will be dispersed, it will be scattered, and it will attenuate. And that's what we call unguided media. So the radio channel and satellite channel, these are unguided media, whereas those twisted pair copper wire, coaxial, and fiber optic link, they're called guided media. Now let's look at this twisted pair copper wire. Twisted pair copper wires is now the best choice for local area networks because it gives you more bang for your bucks. Okay? If you want speed, you want low cost, but of course physically connected, then twisted pair is the way to go. In the 1980s, when fiber optic links first came about, people thought twisted pair copper wires will eventually disappear because think about it, you can travel either the speed of light or travel maybe 2/3 the speed of light, or speed of light. But the problem is, using optical fiber connections will require specialized modem that will handle this dipole, which is very expensive. Let's look at the different wires that are commonly used. We have category 5. The thickness of the wire dictates the speed, the link bandwidth. If you want to avail up to about 1 gigabit per second, then you have category 5. What is better is category 6A, which is thicker and it can carry signals up to hundreds of meters, and you can avail of 10 gigabits per second bandwidth. Okay. So as I mentioned earlier, the rate of transmission is directly proportional to the thickness of the wire and your distance from the transmitter. In the internet, what we're using is this twisted pair copper wire, and at the end we have what we call RJ45. RJ stands for registered jack 45, and it's a standard. And what we're using is that it's got a bundle of those wires, twisted pair copper wires, and we're normally using the unshielded twisted pair copper wire. Coaxial cables, as I mentioned, offers better bandwidth. It's using copper wires as well, but the arrangement of the conductors are in concentric form. There's one conductor here and another conductor here, and they're properly insulated using some sort of plastic medium. Okay. This has better capacity than twisted pair copper wire, but more expensive, and that's what we mentioned earlier. It is used for a shared access network. Okay. What about they also allow for bidirectional use. You can transmit and receive at the same time. Let's look at the fiber optic cable. Just want to check the time. How many more minutes? We will be dismissing in 2 minutes. I just want to talk about this fiber optic cable. Just a little bit of some concepts from physics. Let's talk about this fiber optic line. Fiber optic cables are flexible glass fibers. Okay? And the figure here tells us that. Okay? That's how they look like. One light pulse is equal to 1 bit. And inside this fiber optic link, light will be traveling. Okay? This operates using the principle of total internal reflection. So light bends inside, okay, by using a more dense medium and a lesser dense medium. Since you're propagating light, fiber optic links are immune to electromagnetic noise, electromagnetic interferences, and you can connect to the internet with hundreds of gigabit per second bandwidth, even if you're hundreds of meters, hundreds of kilometers away. Okay, So this is of course the preferred medium for the internet backbone, okay? So it makes sense. And you can avail of hundreds of gigabits bandwidth. We will have to stop here, unfortunately. We will